This lesson is focusing on indices. Just like the four main arithmetic operations used in maths, which are addition, subtraction, multiplication and division, exponentiation is a type of math operation. Indices are used in exponential functions and tell us to take a number and multiply it by itself a certain number of times. You can remember it easily as repeated multiplication. Let's look at an example. Here we have taken the number 5 and multiplied it by itself 3 times. As you can imagine, this can become quite a long process, so we can use index notation to display it clearly and quickly. To write this example in index notation, it becomes 5 to the power of 3. The base is the number that is being multiplied, which is 5. So that's the base. And the index is the number of times it is being multiplied, which in this case is 3. Let's take a look at another example. So here we have 3 times 3 times 3 times 3 times 7 times 7. You can only group together the same numbers. So in this example, the 3's will be grouped and the 7's will be grouped. So this will become 3 to the power of 4 times 7 to the power of 2. Now that we understand index notation, we can move on to learning the index laws in order to take some shortcuts. So index law number 1. Let's have a look at this example. So here we have a to the power of 3 times a to the power of 2. To understand what the law is and where it comes from, let's write it out in expanded notation. So here we will get a times a, which is a to the 3, times a, which is a to the 2. Now we can group all the like terms together and we'll get a to the power of 5. Can you see a shortcut from the beginning expression? Instead of writing it out each time, in this case we can add the indices. So if I put this in brackets, we can go a to the power of 3 plus 2 is equal to a to the power of 5. Let's write this as a general rule. So we get a to the power of m times a to the power of n is going to be equal to a to the power of m plus n. Looking at one more slightly different example, we have 4a to the power of 3 times 3a to the power of 2. The numbers in front of the variables follow the usual rules of multiplication or division, but the index numbers follow the rules of indices. So we multiply the 4 and the 3, and we add the indices. And this becomes 12a to the power of 5. Moving on to index law number 2. So we have a to the power of 5 over a to the power of 3. Again, to understand what the law is and where it comes from, let's write out this example in expanded notation. So on the numerator we get a times a times a times a times a, all divided by a times a times a. So using our timetables, we know that a divided by a is equal to 1. So these terms cancel out, leaving just a times a. So let's cancel those out. And we're left with just a times a. And putting this into index notation, we get a to the power of 2. So writing this as a general rule, we get a to the power of m divided by a to the power of n is equal to a to the power of m minus n. So just a side note, take care when multiplying and dividing expressions such as y times y to the power of 4 or z to the power of 3 divided by z. This is because y is the same as y to the power of 1, So therefore, when y times y to the power of 4 is equal to y to the power of 5, because you add the indices. And same as with this one down here, we have z is equal to z to the power of 1, therefore z cubed divided by z is going to equal z to the power of 2, because you subtract the indices. So moving on to index law number 3. So our example here is in brackets a cubed, close brackets, squared. So again, let's write this out in expanded notation to understand where the law comes from. So we get a to the power of 3 multiplied by a to the power of 3, because there's two lots of them. So we can expand this a little bit more. So now we're going to expand those brackets. So a times a multiplied by a times a times a. So now when we group all those like terms together, we'll get a to the power of 6. So having a look at the original expression, can you see the shortcut where we get to this answer here? So instead of writing it out each time, we can multiply the indices. So I'll just put that in over here. So a to the power of 3 times 2. So writing out our rule is, so we're going to have a to the power of m in brackets to the power of n is the same as a to the power of m times n. So our last law is index law number 4. This example is in brackets ab, close brackets, to the power of 2. So let's write this out in expanded notation. So we will get ab times ab. So when we group our like terms, we will get a squared times b squared. So instead of writing it out each time, what we can do is we can raise each number inside the brackets to the power of that outside the brackets. So writing that as a general rule, if we have a, b to the power of m, that's just going to be a to the power of m multiplied by b to the power of m. We can extend the definition of powers to zero, negative, and fractional indices. A meaning for the zero index can be demonstrated as follows. So in this case, 3 to the power of 4 divided by 3 to the power of 4, we can apply the second law. So we will get 3 to the power of 4 minus 4. Then that will give us 3 to the power of 0. But we also know that 3 to the power of 4 divided by 3 to the power of 4 is equal to 81 divided by 81. And we know that 81 divided by 81 is equal to 1. So to be consistent, we should have that 3 to the power of 0 is equal to 1. This demonstration could be repeated for any base except 0. So we say that a to the power of 0 is equal to 1. Similarly, we can demonstrate a meaning for a negative index. Suppose a to the negative n did exist. Then we could write a to the power of n times a to the power of negative n. And using our laws that we already know, that would be a to the power of n minus n. This then equals a to the power of 0, which equals 1. This shows that a to the power of negative n is equal to the inverse of a to the n. So writing that as a rule, we get a to the power of negative n is equal to the inverse, which is 1 over a to the n, and vice versa. So a to the n is equal to 1 over a to the negative n. So let's look at an example. So here, express with positive indices. So for a, we have 1 over a to the power of negative 8. So writing this with positive indices, we're going to write it in the inverse. So we will write this as a to the power of positive 8. B, we have a to the power of negative 2. So writing this one with positive indices, follow this rule up here, and we get 1 over a to the 2. So moving on to looking at fractional indices, we have a to the power of 1 on q in brackets to the power of q. So to find the definition of a to the power of 1 on q, we can do the following. So a to the power of 1 on q in brackets to the power of q is also equal to a to the power of 1 on q times q. This simplifies down to 1, so this becomes a to the power of 1, which is then equal to a. So a to the power of 1 on q to the power of q would be a, following this example. In other words, for the laws to be consistent, a to the power of 1 on q would have to be the qth root of a. So let's write that rule down here. So a to the power of 1 on q is equal to the qth root of a. So let's do a quick example. So here we have a to the power of a half in brackets, all squared. So we can rewrite this as the square root of a squared, because a to the power of a half is the same as the square root of a, and we know that the square root and the square cancel out and we're left with a. You can also have other fractional powers, not just 1 to the q, but p to the q. So looking at this example up here, we have a to the power of p on q. This can be rewritten as a to the power of p, all in brackets to the power of 1 on q. And therefore, following the same rules, we can rewrite this as the qth root of a to the power of p. So looking at a quick example, so looking at b, we have b to the power of 7 on 3. And following the example from above, to express this as roots, we would write it as 3 square the root, so we say this is cube root, v to the power of 7. Thank you for watching. The next video following on in this unit will be on binomial expansions.